Okay, so there's that function with its domain restriction. That's what that's called here, is a domain restriction. So it'll only let us use certain x values. Let's talk about this function here. So what type of function are we looking at? What family of functions are we looking at here? What would the graph of this look like? Okay, it's a square root. Okay. Our family of functions is a square root. Are there numbers that we can't square root? No negatives, right? Why can't we do negatives, Katie? Make sure you're speaking to the class, not just me.
Negatives are imaginary numbers.
Yeah, so square roots of negatives are imaginary, so we can't graph them. We can calculate them, but we can't graph them. Can we square root 0?
You can't square root 0.
Can you say that again, Grant? I couldn't say if you said Grant can or can't.
I don't think you can.
No? Is there no number of times it's that equals 0?
No, there are not.
I bet you could think of one, Grant.
0.
Yeah, so 0 is square rootable, right? So, but we can't square root negatives. Okay. Are there numbers that we would rather square root than others? Okay, yeah, probably don't want to square root decimals too much. We can square root decimals, but we probably don't want to so much. Can you be more specific, Rhea? It'd be helpful if you guys send me a lot of private chats. It'd be helpful if you speak to the class. The numbers that we would rather square root than others. Perfect squares, like what, Maddie? Okay. So we say 16, Maddie, but why would we actually not want to square root 16 here?
Because it's off of the graph.
Yeah, so it would work nicely. Just we couldn't use it. So what would work for us then, Maddie?
4.
4. Okay. What else?
Everything else is off of the graph.
No.
8.
9. Yeah, 9. One more.
12. That's off of the graph.
12 is not a perfect square either. Yeah. It's another perfect square that we could use. Yeah, 1, right, Riley? Okay. So these are the numbers that are easily usable, right? Any number that's bigger than 0 or 0 or bigger would be fine. Okay. But these are the ones that are the easiest to use. Okay. If you want to plug in 5, plug in 5. You want to plug in 7, plug in 7. Okay. But these are just the nice ones. So we get 0, square root of 0 plus 3 is 3. And square root of 1 plus 3 is 4. Square root of 4 plus 3 is 5. Square root of 9 plus 3 is 6. Okay, so just plugging the numbers in. Okay, and spot those points. Again, guys, when you're graphing, at the very most basic level of graphing, you are picking x's to plug in to get y's, right? If you're careful about the x's you pick, you'll get nice y answers. If you're more random, you'll get decimals, but they'll still be points. You can still graph decimals. Right? It's just they won't be pretty, it'll be a little bit more work. Right? But you can still get the job done. Okay? So that's most basic level, throw x's at it, get y's out, plot the points. Okay? So x can't be less than 0, which means there's no arrow on the left side. Okay, just like the blue one had no arrow on its left side. So remember that square root graph is that half curve off to the right. Okay. So there's our graphs. What's the domain of each of these guys? So domain, what's the range? Domain, range. So domain, x values, left to right. So my leftist point on the blue one here is 3. Get a bracket. It's the rightest point, infinity. Range, lowest to highest. So the lowest value on the blue graph is 0. Highest value is arrow up forever. Okay. Make sure you have bracket 3, comma infinity. Make sure you have bracket 0, comma infinity. Parenthesis on those infinities. What's the domain of g of x? Wesley, what's the domain of g of x? Cole, what's the domain of g of x? Tiger, what's the domain of g of x? Zero to infinity, right, Elijah? Or Elijah, on your computer, if you wanted to hit option 5, that will do the infinity sign for you. Or I'd be okay if you just typed like an INF. Again, you should also put that in the public chat. Okay. Colby, where do we get? Oh, okay, Doria. Where'd you get 0 from, Elijah? Victoria's asking where you got 0 from.
The leftist point on the green, like, graph thing.
Okay. Does that help, Victoria, or are you still confused?
Can you hear me?
I can't hear you.
Okay, sorry, my computer just glitched. No, I understand that now. I was just confused.
All right. So Victoria, what's our range?
Is it G infinity?
Yeah, I can barely hear you, but I think I heard you 3 to infinity. Okay. So what do you guys notice there? Looking at the domains and the ranges, what do you guys notice? Yeah, so it's like flipped, right? And so this is something we'll talk about later, but you guys should notice that. Yes, okay. All right. So there's our domain range. All right, this last thing. So f of g of x. This has been a while since we've talked about this. It's been a while since we talked about function composition. Okay. So taking a function of another function, right? So f of g of x. Let me get back up here. So f of g of x. So what that means that we want to do is take g and shove it into f. Okay, so that x there is going to be gone. It's going to be replaced with that new function. Okay, so when I look at f, it's something minus 3 squared, right? It's just now that our something is now going to be the square root of x plus 3. Let me zoom in there. Okay, so the x that was in f has been replaced with all of g. Okay, we've done this, it's just been a while. Okay, you guys recalling that? Okay. So now we want to simplify that. What's this equal to? Okay, so if we're going to simplify, we're just going to follow PEMDAS. Okay. What's this equal to? Simplify it down. Okay, we're not solving for x or anything like that. Okay, just simplifying. So we go inside those parentheses. Okay, inside of here, there's nothing for us to do. So we have to go on the outside of that. Outside of that, there's no exponents. Outside of that, there's no multiplication or division. But outside of it, there is subtraction. So I'm looking at this. What can this do? Well, plus 3 and minus 3. Those can interact. And when they do, they cancel. So I get down to square root of x squared. Okay? And I reset my PEMDAS. Inside the parentheses, there's nothing to do. So then I go on the outside of the parentheses. Oh, there's an exponent. Okay? Well, if I square a square root, what do squares and square roots do to each other? Yep, cancel. So what are we left with? X. Okay? So f of g of x equaled x. So when I plug g into f, and I simplified it down, just spit x back out. Okay? Try to do that here, see if I can not write so big this time. I'm going to do it the other way around, right? The other one said to define g of f. So g of f of x. So what does that look like? So g of x, so starting with the outside one, was the square root of something plus 3. Okay. Well, the something is now what f was, or is. F is x minus 3 squared. So I have the square root of x minus 3 squared plus 3. Okay. And then we want to simplify that down. So again, we're following PEMDAS here to see what we can do. Okay. Inside the parentheses, there's nothing for us to do. Outside the parentheses, we have 2 exponents. Remember, a radical is an exponent, so it's a fraction exponent. So these 2 exponents will interact, right? And we already talked about how squares and square roots cancel each other. So those 2 interact first. So we get x minus 3 plus 3. And then, of course, x minus 3 plus 3. Those will then cancel. That would equal x. So g of f of x would also equal x. So what we just saw here, and this isn't something you guys have to worry about too much, is how you prove if functions are inverses of each other. That if you plug them into each other and both times they reduce down to x or simplify down to x, then those are inverse functions. Okay? You do have to check both of them. You have to do f of g and g of f. You can't just do one. Because there are some functions, not a whole bunch, but there are some functions where I could plug g into f and it would go down to x, but then when I do it the other way, it doesn't go down to x. So you do have to do it both ways in order to show that they are, again, prove that those are inverses of each other. Okay? Again, not something you guys really have to worry about. Okay? So we're going to formalize a lot of these ideas on the next page. I'll come back at certain points to say, like, here's how we saw that show up during our example there. But the next part's going to be kind of like an information dump about inverse functions and like their properties. And then I'll come back and say, here's how we saw that show up here, you know. Anything here you guys want to talk about before we go on to the information? Yeah, thanks, Ruth. Okay, so characteristics, relationships of inverse functions. Start off with just a notation thing. So f inverse of x. That's how we write that. Okay. F inverse of x. So this symbol right there stands for the word inverse. Okay. We don't say f to the -1. Okay. We say f inverse of x, or we can say the inverse of f of x. Okay. We don't write it like this. Okay, the -1 doesn't go at the end, it goes on the f. Okay. The other thing, so we got to be really careful because we've used that notation before and it meant something completely different. So you got to be really careful about cutting that off when we look at this stuff. Okay. When we talked about negative exponents before, like if I said, what's x to the -2, what did that mean? Okay. That does not mean this. Right? Negative exponents meant fractions, right? So this notation does not mean that here. Okay? This is not an exponent. We're purely using that symbol to stand for the inverse. Okay? That was the whole point of there. They're not trying to mean something else by it. So you just got to be really careful about mixing those things in your head. Okay? It's going to be really important that you guys read this to yourself correctly. When you look at this, that you say f inverse of x. You need to say it. Because if you don't connect this symbol with that word, and I say, hey, find this, you're not going to have any idea what to do. Okay? So this means the word inverse. Okay? This next part's pretty dense, and part of the problem is that it's going to involve a definition of something else that we haven't really talked about too much before. So kind of have to do like a double definition here of what it means to be one-to-one. Like it's not something that we really talked about. So I'll have to talk to you about what it means in relationship to inverse functions, and then also mean like what does it mean period. So but how it relates to inverse functions is basically saying if f of x is one-to-one, I'll define that here in a second. And f of x equals y, right? So we have a function, it's a one-to-one function, which is a special type of function. And then we plug a number in and we get a value back out, right? That's the second part's pretty normal. F of x equals y. Then f inverse of y will equal x. And this will make more sense when we do the next one, like far as like when we put some numbers into it, this will make more sense. So this is a kind of like a dense looking definition. It might not make super much sense, okay? But I think once you see the point relationship, it'll be pretty clear once we throw a number at it. But what does it mean for a function to be one-to-one? So for something to be a function, for a relation to be a function, that's what we talked about, like the vertical line test. Each input has only one output. Okay, that's just being a function. Now, if you're one-to-one, each output comes from only one input. So the first part of that is, what does it mean to be a function? The second part is, this is a one-to-one function. So every input only has one output. Output only comes from one input. So that's why they use the term one-to-one, because it's one this way and it's also one this way. So basically what, like things that you guys would think about that aren't one-to-one, like things that we've talked about a lot that aren't one-to-one, would be like a quadratic. And how you guys are going to use this, like it's really not that bad as far as what you guys need to do. You're going to run what's called the horizontal line test. So if we imagine like graphing a quadratic, if you run a horizontal line through it, just like the vertical line test, if the horizontal line hits it twice, then that function will not have an inverse. Okay? So if the function is not one-to-one, it won't have an inverse. So we could not find the inverse of that function right there. So that function is not one-to-one. Things that we've talked about that are one-to-one, something like cube. Like if I did x minus 3 cubed. That would look something like this. That function is one-to-one. Horizontal line test only hits once. Okay. So as far as what you guys are going to need to do, you'll just need to check to see if a function is one-to-one or not, and you'll just do that by graphing it using Desmos or whatever, and just see if it passes the horizontal line test. That's it. If it's not one-to-one, then you can't find its inverse. You'd be like, okay, I'm done. I don't need to do anything else. Can't do anything else. Okay. So how that relates back to what we did earlier, notice that we had x minus 3 squared, right? A quadratic. But this is why this happened, why they said that x could only be 3 or bigger. Because if we did any numbers that were less than 3, they would have started to move up on this side, and then they would have, that horizontal line would have crossed twice, right? Because the other side of that graph looks something like that. And then all of a sudden, we don't have a one-to-one function anymore. So what times they'll do if with functions like this, if they want them to be one-to-one, is they'll do what's called a domain restriction, which is what this was. They said, hey, you're only allowed to use these certain x's. Okay? And the higher level of this stuff would be for me to give you guys a function and say, hey, find its inverse. If you need to, restrict its domain. Okay? I'm not going to take you guys there. All right? If I have you give you guys a function like this that would need to be restricted, it'll already be restricted. Okay? You guys don't need to worry about that side of things. But the main thing here with this is the point relationship. This is probably one of the biggest things that goes on here with inverse functions, like why you want to know about them. Okay, and I'm just purely making these numbers up. Okay, if f of 2 equals 7, then f inverse of 7 would equal 2. So that idea that the functions undo each other, that whatever math is happening to 2 to get 7, right? So I plug 2 into f, I get 7. I plug 7 into f inverse, it undoes that math and spits the 2 back out. Okay? If I take $2 and I get 7 euros, then 7 euros must be $2. 2 degrees Fahrenheit is 7 degrees Celsius. It's not. Then 7 degrees Celsius must be 2 degrees Fahrenheit. It's not. Okay? So it's the undoing. Okay? Again, just another example, but just making up numbers. If f inverse of negative 3 is 0, then f of 0 must be negative 3. And we actually already saw that happen. We just didn't make note of it. Okay, so I'm going to flip back. Here's the point relationship. Okay, 3, 0, 0, 3, 4, 1, 1, 4, 5, 4, 4, 5, 6, 9, 9, 6. Okay, the x's here are the y's here. The y's here are the x's here. Okay, direct translation every single time. I guess it's not direct, but right, inverse translation every single time. So if I know the points that are going to give me f of x, then I can very easily find the points for f inverse. I don't have to do a whole bunch of work. Okay? Anything there with the first 3 you guys want me to clarify before I move on to the last 3? The domain range relationship, somebody said earlier, and then it's really just an extension of the point relationship, right? All of the x's of f will become all of the y's of f inverse. All of the y's of f will become all of the x's of f inverse. Okay, so the domain of f of x is the range of f inverse. So it's basically just taking the last relationship and just expanding it, saying, well, if it's just those x's, it's also all of the x's, right? And then kind of vice versa, the range of f of x is the domain of f inverse. Composition one here, again, you guys don't need to worry about too much. It's what we saw, though, that if we plug one function into the other, they will reduce to x. So f inverse of f of x would give us x back out, and f of f inverse of x would also equal x. Again, that's how you would prove that a function and another function are inverses of each other, that both of those would have to work in order for that to happen, and not something you guys really need to worry about. We won't be doing a lot of proving. I'll be more having you guys find inverses, or given a graph of one, like, find the graph of the inverse. Or given a point in one, find the the point in the other one. And then the last one, the symmetry. This one will be kind of important to you guys, like, as far as the graphing goes. The graphs of f of x and f inverse are reflections across the line y equals x. So it's not as simple as like a vertical reflection or a horizontal reflection or something like that. They're reflected across this line y equals x. I'll go back to the other page here in a second and show you what that looks like. But again, I will give you guys like a graph in the web assign and ask you guys to see if you can pick out the graph that is its inverse. And this could be one of the tools you use to do that. You could also use the point relationship to help you do that as well. So let's see how that applies to the graph that we already did. So the line y equals x, right, it's a line, right? Its slope is 1, its y-intercept is 0. So it would go from corner to corner. I'm very happy with how I did that. Okay, so there's the line y equals x. So what you want to notice is if we look at the green graph, so the part that's on the left side of the green graph gets reflected to this part here. Okay, I'm not looking here to here. I'm not looking at green graph to green graph. I'm looking at how the green graph compares to the blue graph. So these two parts are reflections of each other across that line. And then these two parts here are reflections of each other across the green line, or across the line. It can be kind of hard to see sometimes when the graph does cross the line of symmetry, how that acts. But so that's why I'm looking at it in sections, so that this section reflects to this section. If the function does cross the line of symmetry, then the inverse function will also cross the line of symmetry at that exact same point. So see how these all converge here at this one point. That will always happen. So if you cross the line of symmetry, the other graph will also cross at that exact same point. So they'll always meet like that if that happens. They don't have to cross, but if they do, they always meet like that. Okay? So it's not as simple as like a vertical reflection or horizontal reflection, like seeing if they're symmetrical, but there is a way to do that. Okay? You can also use the point relationship to help you. If you have this point here, you can say, okay, well, its reflection would be at 3, 0, right? If I have this point at 4, 5, then its reflection must be at 5, 4. So you can also use that to help you find the new graph. So those are kind of the features, the relationships when you look at characteristics of inverse functions. Try to point out to you guys which ones will be more important to you. But the main bulk of your work is going to be given a function, finding its inverse. That's what we're about to practice next. Anything you guys need here? So again, that if I say here's, so here's your function, okay? Okay, here's your function, find its inverse, okay? First thing you want to do is see if it has an inverse. Is it 1-to-1? So you're going to graph it, and you're going to check to see if it passes the horizontal line test. Okay. If it hits the horizontal line, hits it more than once, the problem is not doable in the way that I gave it to you. Okay. If I said, here's this function with this particular domain, then you'd have to look at that, just like we did on the first problem. Okay. So you graph it, check the horizontal line test. Next thing you want to do is write it in y equals format. So instead of f of x equals 2x plus 11, it would be y equals 2x plus 11. So that's all that means. Just change it from f of x to y. Okay. The reason we want to do that because this is the key step here. You want to switch all the x's and y's. So instead of saying y equals 2x plus 11, it's going to say x equals 2y plus 11. If that had said like y equals 2x squared plus 5x, then it would need to say x equals 2y squared plus 5y. So every x would need to become a y, every y would need to become an x. Okay, so make sure they all get switched. Once you have it switched, you want to then solve for y. But solving is a pretty nebulous statement. Okay? It's a pretty big thing. There's lots of tools you guys have for solving. Is it just getting y by itself? Generally, yes. That's all you need to worry about is how do I get y by itself? Okay. But do I need to do some factoring here, right? We know that factoring is a way of solving some things. Okay? Do I need to do square roots? Like, you guys have lots of tools for solving. So you need to be reaching all in there and figure out what it is that you need to solve each individual problem. It's going to change from problem to problem. Okay, so there's going to be a lot of mental flexibility on your part here. How do I get y by itself? Once y is by itself, you're going to rewrite it back into the function notation. Except for now you're not going to say f of, you're going to say f inverse of. Okay. So step 2 being get the f of x out. Step 5 being put the f of x back in. But now you're saying here's my inverse function from where I started with. And then step 6, when it says sketch, that would basically be like your check. If you take your function and then you go find its inverse and then you sketch them and they don't reflect cross the line y equals x, then you messed up somehow. They aren't inverses of each other. The other way you could use the check would be to do the composition. But most people prefer to do the sketching as it's not as difficult. Can actually sometimes be more time consuming, but because you're graphing, but it's usually less thinking. So step 1, check to see if it's possible. Step 6, check to see if you did it right. And step 2 and 5 through 5 are really where the math is. Really, step 4 is where all the math is. But step 3 is the key step. Okay. Anybody need more time here to get steps written down? All right, let's go and do that. I know we're not going to finish today. We'll finish tomorrow, hopefully like in 10 minutes. I'll give you guys the rest of time in class tomorrow to work on homework, and then I'll go and extend the assignment into the weekend, but I'm not going to give you time on Monday to do it. So it really will behoove you guys to make sure you look at the assignment tonight and make sure you come with questions. If there's, obviously you won't know everything yet, but you'll want to make sure you're ready to ask questions on if I don't cover something tomorrow. And obviously you can see the examples we're going to cover and how they might relate to the ones that we're going to do, when you have homework. Definitely something you guys need to make sure you're doing is making sure you're reading that correctly. Okay, if you don't read that correctly, you're not going to know what it's asking you to do. Okay, find F inverse. Find the inverse of F. If you don't attach that word inverse to that symbol in a week and a half or something like that, when we're taking a quiz over this, you're like, I don't know what to do. You don't know what that's asking you to do. Okay, so make sure you're reading that to yourself. You really do need to say it in your head. Okay, out loud. Okay, what are you being asked to do? So here's our function. First step, rewrite it into y equals 4x plus 3. Key step, switch x and y. X equals 4y plus 3. Okay. Step 2 is really easy. Oh, we didn't do step 1. Crap. Okay. Is it 1-to-1? All right. Is this even doable? What's this a graph of? If we graph that, what are we going to get? Y equals 4x plus 3. What is it? It's a line, right? Okay. Is that line going to be 1-to-1? Does it pass the horizontal line test? All right. It's only ever going to hit once. Okay. So yes, it is 1-to-1. All right. So this problem is doable. Okay. So just check that real quick. So make sure we're not wasting our time. It is 1-to-1. Boom. Check. Okay. Get y by itself, right? That should be pretty easy with a problem like this. Subtract 3 from both sides. X minus 3 equals 4y. Divide by 3. Divide by 4, not 3. So I noticed that on the right side, the y is going to be by itself now. So I'm going to go ahead and kick it to the left side. So I get x minus 3 over 4. You guys could leave it this way and be fine. I probably would suggest that you go ahead and rewrite it as, like, since this is a line, rewrite it into slope-intercept form so you can make more sense of it. 1 over 4x minus 3 over 4. Okay. That should mean more to you, because if you're in a graph, I mean, would you rather graph from this form or would you rather graph from this form? Okay. So just something to think about. This is easier to graph from. So if part of your job is to graph, then you probably want to go and do it like that. Okay. But if you left it here mathematically, that is correct. Okay. So the last step is to rewrite it as the F inverse Okay, so make sure you put the proper notation on it. But they can be pretty easy like that, right? Just solving a linear equation should be easy for you guys, right? Here you're solving a square root equation. How do you do that? The last one's the trickiest, okay? But solving, right? Domain and range for both. What's the domain for a line? When I graph a line, what's its domain? Yep, infinities. All reals, negative infinity, positive infinity. Okay, what about its range?
Would it be negative infinity and positive infinity?
Mm-hmm. Lines are pretty easy. They go left and right forever. They go up and down forever. Okay. So if you left this one like this, which again is fine, we can do that. Okay. You might have a hard time seeing this as being a linear equation. It doesn't look particularly much like a line equation, right? You might not look at that and go, oh yeah, that's a line. But it is a line because the exponent's a 1. That's all that matters. Okay? But you're not going to see it. So you might struggle with that saying, oh, what's the domain and range of that? I don't know. Whereas you might look at this way, oh yeah, I can find its domain and range easily. If you left it like this, you could be kind of in trouble. Well, remember, you don't need to know the domain and range of this in order to figure out the domain and range over here. If the domain of f is this, then what does that tell us? If this is the domain of f, what do we then know? The domain of f is negative infinity, positive infinity. It's the same as the range. Ruthie, I'm going to finish your sentence for you. It's the same as the range of the inverse. Okay? So if you know the domain of the original function, that means you know the range of the inverse function. Okay? And in the same way, if you know the range of the original function, that means you know the domain of the inverse function. So hopefully you get my statement here when I say you don't need to know them to know them. Okay? I don't need to know what these are to know what they are. I just need to know what these are in order to know what these are. Okay? Does that make sense? So if you're all struggling to find the domain and range of the inverse function, just use the domain and range of the original function to help you. Okay? All right, last thing, let's graph these boogers real quick. So the original function, it's a line, 4x plus 3, y-intercept is 3, slope is 4, so rise 4, run 1, fall 4, go backwards 1. So we got a line here. The other one's a little bit trickier to graph since it does have a fractional y-intercept. So down negative 3/4, but rise 1, run 4. Rise 1, run 4. Fall 1, run 4. But it would look something like that. I'm going to do that red. So there's F inverse. It did ask us to label them, so we need to be careful about that. Since we are doing 2 graphs on there, we wanted to make sure we label them. So F and F inverse. And then if we drew that line y equals x, just to check to make sure they are actually reflections of each other, just go corner to corner. And you should do this one dashed because it's not actually there. So then you can see that this portion of the green graph reflects to this portion of the purple. And these two reflect in each other. This portion of the purple graph reflects to this portion of the green graph. Notice how they all meet right there at one point. Okay. So yeah, we can see they actually are reflections on each other. All right, thanks for sticking with me there. We will